So when we are considering or are thinking about lunar evolution, there are three main phases that I'm primarily interested in. One is the establishment of the Earth-Moon system from the giant moon-forming impact, differentiation, and volcanism, basaltic volcanism. And what's unique or interesting to me about each of these stages is that they include a significant amount of outgassing of volatiles and, in some cases, the production of transient atmospheres. When we consider the environments that existed on early Earth or early Mars, what we know is that there was also a significant amount of outgassing from volcanism, and particularly in terms of sulfur, there was the interaction between gaseous sulfur species and UV UV spectra that resulted in the distribution of various sulfur compounds across both Mars and Earth. And particularly in that interaction between ultraviolet spectra and gaseous sulfur compounds, what we found in the sedimentary rock record is that the rocks preserve a fingerprint of how the atmospheres of early Mars and Earth have evolved and the types of chemistry that's occurred in those atmospheres. There's also the environments in which sulfur is processed in the early solar nebula. And what we have determined from the sulfur isotope analysis of differentiated meteorites is that there's the processing of gaseous sulfur compounds and interaction with ultraviolet spectra and the incorporation of that sulfur into the deep interiors of planetesimals. And so given that there are environments during the moon's evolution that includes a lot of production of gas and interaction of gaseous sulfur compounds with UV from the sun, it leads us to ask, well, is there any evidence in lunar materials of any sort of atmospheric volatile processing like that seen in early Earth, Mars, or even in nebular environments? We also have identified or have characterized various meteorite groups and have determined that the CAP33S, the mass-independent tracer, can be used to define different parent bodies. And therefore, as we characterize different lunar materials, we can then test whether there is a genetic link between the Earth and the Moon through the sulfur isotope characterization of Earth and Moon mantle materials. Through our characterization of lunar basalts, what we find is that the Delta 34S composition is different from estimates of bulk silicate Earth. Now, this is a mass-dependent tracer, and what this is illustrating is likely fractionations associated with planetary differentiation or potentially some volatile loss. But what's most important here is that the CAP33S, the mass-independent tracer, is no different between the composition of bulk silicate Earth and lunar basalts. And so this has led to suggestions, at least in terms of sulfur, that the Earth and the Moon are genetically related. Soon after the publication of that material on lunar basalts, we published data on lunar soils. And most excitingly, in our analysis of sieved lunar soils from 75081, we found a relationship between the sulfur isotope composition and sieved grain sizes, where the largest grain sizes have a sulfur isotope composition that appears most closely matched with lunar basalts, and the smallest grain size fractions have a more fractionated sulfur isotope composition, where the fractionation in Delta 34S is likely linked to atmospheric escape of sulfur that was first released during a micrometeorite bombardment event. And simultaneously, as that gas was produced and sulfur was lost to the atmosphere, there was the interaction of gaseous sulfur with ultraviolet spectra, and ultimately that gas then condensed onto the soil grains. And so in this scenario, what we then determine is that, okay, there is some sort of similarity between volatile processing and transient atmospheres on the moon that matches some of the chemistry that occurred on early Earth and Mars. But this is way later in the moon's history. We're still interested in events that occurred much earlier that could mimic some of the similarities between the evolution of Earth and Mars. Following that publication in 2022, we then published data on sieved lunar volcanic glass beads from the double drive tube 74002/1. And unlike the soil grains, what we identified was that the delta 34S values were fractionated towards negative values. And instead of a fractionation associated with atmospheric escape, it was a fractionation associated with volcanic degassing. And also what's different from the lunar soils or regolith material is that we don't see the same trend that highlights a correlation between grain size and sulfur isotope composition. And instead, we see no difference in the CAP33S composition of large grain sizes and small grain sizes. And further, this CAP33S composition, although it is small, is distinct from that associated with lunar basalts. And so this led us to a suggestion that the lunar mantle may be heterogeneous in terms of its sulfur sources. However, we were left questioning how any sort of atmospherically processed sulfur component could be delivered to the lunar mantle and preserved throughout all of the various mantle evolutionary processes that we know likely occurred. This then led us to take our study from bulk measurements of sulfur isotope compositions of lunar materials to looking at the sulfur isotope composition in situ. And through the ANSWER program, the lithics fragments teams and the rest of the ANSWER science team, we analyzed a variety of sulfides from different lithic fragments, ranging from felsites to noritic and northicites, plagioclase grains. And what we find is that some of these grains do preserve really strongly fractionated or mass independently fractionated sulfur isotope compositions. And these are compositions that would lend credence to the fact that there is source heterogeneity of sulfur components in the lunar mantle.
1 minute left.
Now, sorry, what? 1 minute? Okay.
1 minute.
Now, while I guess we've ruled out that the sulfides are most likely endogenous and not related to some sort of late stage, fluid sulfur component or added during, a micrometeorite bombardment event, we then would suggest that this would, again, require that there is some sort of mass-independent sulfur that is delivered to the lunar mantle. And we now have unambiguous evidence that there's likely source heterogeneity of sulfur components. But we're still left wondering how this component could be transported to the lunar mantle. Perhaps the signatures are a relic of, a nucleosynthetic anomaly, or delivered by some large impactor that then didn't mix well with the rest of the lunar mantle. Or perhaps there wasn't some sort of primitive crustal recycling or delamination of protocrust that had superficial sulfur sprinkled on top that then got transported to the mantle. Now, those hypotheses are not necessarily easy to reconcile with what we know about lunar evolution, but there has been suggestions that the Earth and the Moon do have isotopic differences that could be related to genetic, to not being genetically linked. For example, Kano et al. Show oxygen isotope data and argue that the lunar mantle is is heavier in cap 17O relative to the Earth. Or when you look at the tungsten isotope composition, there's a difference in mu-182 tungsten that's related to, say, a disproportional late accretion events. And considering that our data do show a potential trend in sulfur components and illustrating there's at least two different sulfur sources in the lunar mantle, perhaps it's suggesting that we have a combination of both processes that have occurred. So we can envision a scenario where sulfur was heterogeneously distributed in the early solar system, and perhaps the proto-moon had an exotic sulfur isotope composition. And ultimately, after that proto-moon was established, the composition changed over time through late accreted materials. And since it received less late accreted materials, it's possible that the primitive or exotic signatures were better preserved on the moon than on the Earth. Ultimately, we don't know, and it requires more work. We have the Survey CASA Moon grant, where we're going to dig deeper into the 74002 core. We have students who are in postdocs who will be doing modeling of volatile evolution during the Earth-Moon formation to kind of reconcile my hypotheses associated with sulfur source heterogeneity. And lastly, we need to perform more in situ measurements. There's a paucity of in situ sulfur isotope data on lunar materials, and what we're seeing now is that it is demonstrating that the lunar mantle is much more heterogeneous than we previously thought.